All right, this is an activity that we did in class, and we took a lot more time to discuss. So I'm going to give an abbreviated version. You might need to pause and rewind and probably come in for a little clarification if you need to. But domain and range is such a important topic for this upcoming unit that I spent a half a day discussing domain and range and reinforcing some of the things we've already talked about before. But basically, functions, f parentheses x is pronounced f of x. Functions have an input and an output. And one way to think of them is like a machine, kind of like a vending machine. When you plug in or put in a quarter or dimes or dollars, some machines take credit cards, some won't take dollars. But input, the thing that you're allowed to put into the function, is called the domain or the x value. So the item that can go in the function goes in. The function does something to that item. Say you put a quarter or you put a dollar into the vending machine. It takes that dollar, assesses that it's a dollar, and then it spits something out depending on what you choose. But the machine could, if it's a Coca-Cola machine, it could produce, Mountain Dews, Dr. Peppers, etc. If it's a candy machine, you could get chips or, but the output of the machine is the range or the Y values. And what I've done is given 6 examples here to explore input, output, and then get a little deeper as we go. The first part is just basically plugging in numbers. So I'll illustrate plugging in the domain value -3 into the function x plus 3. When you are inputting that domain value -3 into the function, you are taking the -3 and dropping it into the function. So you'll put it into the function as -3 plus 3. Function tells you to add 3 to your -3, and you get the value 0. So your output value is a Y value of 0. So you get a Y value of 0. That also can kind of show you how the f parentheses x, the f of x, that symbol f of x actually represents the Y value of that specific x that you're plugging in. So if you're plugging in -3, f of -3 equals 0 is the Y value 0. Anyways, that's a little more in depth than I really wanted to get, but let's continue plugging in the rest of them. When you plug in -2 and add 3, you get 1. When you plug in -1 and add 3, you get 2, and so forth. 3, 4, 5, 6. When you plug in to the next function, when you plug in a -3, you'll square -3 and get 9. So you'll get 9 here, you'll get 4, 1, 0, 1, 4, 9. When you plug in f of -3, you get -3 squared, you get 9 plus 3, so you'll get 12 here, 7 here, 4 here, 3, 4, 7, 12. Again, I'm going pretty fast with this because it's something we've done in previous units, and you can pause the video and confirm, check those numbers as you need to. But then we start getting into a little uncharted territory, so we'll break the calculator out to kind of illustrate what's going on when you plug in the function values, the domain values, -3, -2, etc., into the square root of x. The square root of x is the function. We'll go to the table. And you can see from the table, when you plug in -3, it says error. The reason it says error is because the square root of -3 doesn't exist. It's an imaginary answer. And when you're dealing with functions, you only deal with the real answers. So -3 gives you an error. -2 gives you an error. In other words, there is no range value for that domain. What it really means is you can't plug in that domain value. And we'll talk a little more about that towards the bottom. But we continue to plug in -1, and it says error, or we realize, hey, you can't plug in -1. But then when you plug in 0 for the domain, when you plug in 0 for x, you get the square root of 0. You get 0 as the output. When you plug in the square root of 1, when you plug in 1, you get 1 back. So the output is 1. Now there's a star next to the 2 for this reason. Only because we have a calculator do we probably know that the square root of 2 is 1.414. So with the calculator's help, we're able to get that answer. But I've left a couple blanks here to kind of, what would you choose if you didn't have a calculator? What would be good numbers to plug in for x that's under a square root? And one example would be 25, because the square root of 25 is 5. It's an easy mental math problem. So the domain, it also illustrates that the domain is the independent variable. While I've been guiding this discussion and telling you what numbers to plug in for x, it's the independent variable. It's the one that you can put whatever you want in. It's just so long as the function will allow you to put that number in. And as we've seen earlier, you can't put a negative under a square root, but you can put the square root of 16, because the square root of 16 is 4. I would put that in as the domain value. So again, it's just an illustration of domain versus range. Domain, what you plug in; range, what comes out. So the next one, when I plug in -6, I get a -6 plus 5. I get -1 under the square root. So I'll get square root of -1. It will be error. I won't get anything back because that's an imaginary number, square root of -1. When you plug in -5, you get -5 plus 5. You get 0 under the square root. So the square root of 0 is 0. And then -4 would give us the square root of -4 plus 5, the square root of 1. And square root of 1 is 1. Then we get another star here, because if I actually chose to plug in -3, I'd get the square root of 2, to which I don't know the decimal unless I've memorized it or have the calculator to help me, but it was 1.414. So then we think a little bit about what would be a nice number to plug in this situation. Well, the number that we would want to plug in, we're going to add 5 to it, and I'm hoping it's a perfect square. So let's see, 25 is a perfect square. So I would plug in a 20 as the domain value so that it turns into square root of 25, and the output value is 5. The range value is 5. Another example would be plugging in a 4, because when you plug in a 4 for x, you get 4 plus 5, you get a 9 under the square root, which is the output 3. And then we could come up with several other examples, but maybe 31 comes to mind, because if you add 5, you get 36, and the square root of 36 is 6. But again, these basic operation maneuvers, basic plugging in numbers for x, the domain, and getting an output, a range value. But it's an illustration in basic computation, but it's going to lead to a much deeper discussion of domain and range. For the last one, we'll let the calculator illustrate what happens here, and then justify why the calculator says what it says. Because when you plug in -3 to 3 into the function 1 over x, it has an error for 0. And in class, most were pretty quick to realize you can't put a 0 in the bottom of a fraction, so that's why it says there's an error at 0. However, you can plug in any of these other numbers, and when you do, you get the fraction -1/3. 1 divided by -3, -1/3. When you plug in -2 as a domain value, you get the output or range value of -1/2. Then you get -1, 1, 1/2, and 1/3. So then once we filled out those tables, we began then to look at the pictures that were associated with each graph. And then we looked ultimately at the goal of the exercise, domain and range. The sketch of the first picture, I started by graphing the points on the table. -3, 0 would be about there. -2, 1 would be roughly there. 1, 2 would be roughly there. 0, 3. 1, 4. 2, 5. 3, 6. So roughly there. But then I asked, and I'm asking on the video too, is that the sketch of the function f of x equals x plus 3? Is that the entire function f of x equals x plus 3? In other words, y equals x plus 3? And everyone said, no, that's not what it completely looks like, because you, according to them, connect the dots. And I'll use that expression too. Yes, you connect the dots, but it's more of a deeper understanding. Why do you connect the dots? The reason you connect the dots is because you could have chosen domain values of 1.5 or 2.1, and you would have gotten a range value that was a decimal. So when you connect the dots, you're illustrating all those decimal coordinates, all those decimal ordered pairs that you could have chosen, you just didn't. So that's why you connect the dots. A sketch for y equals x squared A quadratic starting at 0, 0 looks like this. The sketch for y equals x squared plus 3 will shift the parabola up 3. We know that from our quadratic unit. But then our next two functions, y equals the square root of x and y equals the square root of x plus 5, starts us into a discussion of the actual upcoming unit and inverse functions. The inverse of adding 5 to my bank account would be subtracting 5 from my bank account. Inverse functions kind of undo one another. So when you think about parabolas and x squared, and you think about their inverse, the inverse of squaring a number is taking the square root of a number. So again, the inverse of squaring a number would be to take its square root. So when we look at the picture of the square root of x, it's going to have a relationship with the picture of y equals x squared. And it's kind of difficult to see on a widescreen TV, which is what this picture is. It's a rectangle, not a square, but it's a parabola. It's half of a parabola turned sideways. So the sketch of y equals the square root of x starts at 0, 0, and it's half of a parabola going to the right. And we'll talk a lot more in the first targets why that's that picture and talk a little bit more about the rest of that picture and when you're talking about an inverse. But this is just, again, an introduction video. When we look at the graph of y equals the square root of x plus 5, we'll notice that this graph shifts to the left 5 units. So when you add a 5 under the square root into the domain of the function, it shifts it left 5, kind of like a quadratic when you have y equals x plus 5 squared plus 3. It's going to move that quadratic left 5 and up 3. We talked about that back in the quadratic unit. But anyways, one more sketch, and I'll let the calculator do all of the drawing for this one. 1 divided by x. Looks kind of funny, but the picture starts really close to the x-axis, then drops down and goes straight down forever, never actually touching the y-axis. And then it jumps up here to the top and comes down and never touches the x-axis either. These are called asymptotes, A-S-Y-M-P-T-O-T-E. There's a vertical and a horizontal asymptote here, meaning that it never touches x equals 0 and it never touches y equals 0. We should really talk a lot more about that, but we just don't have time in this introduction video. We'll talk more about that in the unit. But suffice it to say that it never touches x value 0, as illustrated here. You can't put a 0 in that function, and you will never get a y value of 0 for this reason. The only way you get a fraction to equal 0 is if there's a 0 in the top of that fraction to begin with. And our function has a 1 in the top. So you can't put a 0 into this function, and you can never get a 0 out of the function. All right, and then we moved on to talking about domain and range and answering two simple questions, which we will take separately. First, domain. In answering what's the domain of the function, you're answering this question. What are you allowed to plug in for x? So we'll address that question for all of these functions and pictures. First one, what are you allowed to plug in for x? In other words, what blue numbers are you allowed to put in that table? I chose negative 3. Could we have put a 4 in? Could we have put a negative 4 in? Better question, is there a number we couldn't have put in to the function x plus 3? And the answer is no. Every number can be put into that function, so the domain is all real numbers. With a quadratic, I chose negative 3 as my domain, but I could have plugged in a 4 and got a range value of 16. I could have plugged in a negative 4, and again, there's no number that you couldn't put into a quadratic. So its domain is also all real numbers. Again, we reviewed that the symbol capital R with a couple of vertical lines instead of one vertical line signifies all real numbers. So if you want to, a shortcut, you can use that symbol. Again, for y equals x squared plus 3, I could plug in any number I want for x. There's nothing that's going to stop keep from plugging in a number for x. But then our domain starts to get restricted in the next example. As you can see here, I tried to plug in a -3, a -2, a -1, but I got an error. In other words, the function was telling me, you can't put that domain value into this function. So the domain starts at 0 and gets bigger from there. So the domain is x is greater than or equal to 0. X is greater than or equal to, because it includes 0. Another way you could write that is in interval notation, bracket 0, comma, infinity. That's just another way to say x is greater than or equal to 0. The domain in the fifth function here, I tried to plug in a -6, but it wouldn't let me. It gave me an error. So I think about what number would it allow me to put in first. The -5. That's the number that would make square root of 0 when you plug in a -5 in for x. And that's the first value for which a square root is going to be defined, when you can have a z, where the number that gives you a 0 under the square root. So in other words, the domain starts at -5 and gets bigger from there. So x is greater than or equal to -5. And in the last example, the domain could be anything but 0. That's the verbal expression. You can plug in any number you want into the function 1 over x except a 0. So one way to write that would be all real numbers except x cannot equal 0. I would accept that. Or in interval notation, it would be -infinity to 0, but not including 0, so you use a parenthesis, union, parentheses 0 to positive infinity. And that takes care of the domain. Then we switch over to range for each problem, and we'll be answering this question. What numbers does the function produce when you put the numbers in for x that you said you could put in? So with that, what numbers do we get in red when you plug in those domain values? Well, you get 0, 1, 2, 3, 4, 5, 6. If I plugged in a 4, I'd get a 7. If I plugged in a 5, I'd get an 8. They would keep getting bigger. If I went the other direction and plugged in -4, I'd get a -1 for the range, then a -2, and they would go down forever, meaning all range values are included, so all real numbers for a line. Not true with the quadratic, and we will remember this from quadratics. Our lowest y value is in the vertex here, and it's 0. So all y values start at 0 and go up, so your range for that quadratic is y is greater than or equal to 0. Changes just a little bit in the next example, because the y coordinate of the vertex is 3. So all the y values start at 3 and go up, so y is greater than or equal to 3. We thought just for a moment, could a quadratic have a range that's less than or equal to? And it took a few seconds to think about it, but the answer is yes. These are only 6 examples, right? These are only 6 problems where we're talking about domain and range. Had we been looking at y equals -x squared plus 5, it would have looked like this. Started at y equals 5 and went down. So your range could be less than or equal to in a quadratic. Now let's talk about the range of our fourth graph. We talked about the domain, how you couldn't put in -3, -2, or -1. When you put that 0 in, it gave you an output of 0, then an output of 1, then 1.414, etc. The range values start at 0, start at y equals 0, and go up. So y is greater than or equal to 0. When you look at this next, the fifth function, we finally decided you can't put in a -6, but you can put in a -5. It gives you a 0. -4 gives you 1. -3 gives you 1.41. In other words, the y values start at 0 and they go up. So the range, y values are greater than or equal to 0. And again, with only 6 problems, it's hard to cover everything in 6 questions. So I brought in one more problem here, square root of x plus 3, so that they didn't oversimplify range for a square root and say it's always greater than or equal to 0. Because this one, you'll notice the plus 3 is after the square root. You look at the picture here, your smallest y value will be y equals 3. So your range will be y is greater than or equal to 3. That plus 3 being after the square root affected the range. So again, we'll learn more as we experience more problems and talk about this more throughout the unit about domain and range. But this gives us a much deeper understanding than we had before we started this discussion. And then the last one, this 1 over x graph. I briefly talked about the asymptote situation where it never touches y equals 0, it never touches x equals 0. So what that means, just like our domain doesn't include the value 0, you can't include the value 0 for the domain. We talked about how you would never get a y value of 0. There's nothing that you can put that would make 1 over x become 0. So that means the range has every number except 0 as well. So you could write that as all real numbers, but y cannot equal 0. Or you could write it in interval notation, negative infinity to 0, union 0 to infinity. So again, this is just a little warm-up exercise. I know it's a long video, 20-something minute video, but it's a very deep, it's a pretty deep discussion of domain and range, much deeper than we've had all year long with it, and we will go even deeper with our next unit.